Okay, so we're looking down on the xy plane at a gradient field, and what is special about a gradient field versus just any old vector field? Yeah, Austin.
The gradient field indicates the direction of the greatest rate of change rather than just any rate of change at that certain point, and actually focuses on where it's the steepest.
Okay, so a gradient field implies that there exists what then? So you're talking about greatest rate of change of what? Yeah, so function. So a gradient field comes from and what we call a potential function. So there's this function, this multivariable function, f, and a gradient field comes from that, right? So we know it's the vector of the partial derivatives, right? It's the vector of the partial derivatives. And so that's the gradient field assigned to that. And so it gives us at any point, it gives us the direction and magnitude of greatest rate of change of the surface as a vector, right? At any point. So here's a gradient field. And we're looking down on it here. Here's the z-axis coming up at us. So I want you to make sense of this surface as best you can. So there's kind of some a unique feature in each of the four quadrants, right? And a unique feature in each of the four quadrants that I'm showing you. So kind of make sense of this, and can you try to imagine maybe what the surface looks like from the gradient field? And this is all about discussion, okay? So think about it and definitely talk while I take attendance. Okay. All right, so first quadrant. Caitlin, what did you guys talk about in the first quadrant? What do you see there?
All of the vectors in the vector field are pointing towards a certain point, so it's going to be a maximum.
She's saying that there's a maximum here. This is like a hill, right? Everything's pointing uphill, right? So you got like a hill with like a local maximum right there. Good. Okay. Second quadrant. Paul, what did you guys think about the second quadrant here?
It looks like a saddle point.
Because?
Because they're going up, if you're looking at the up and down line, these arrows can move towards the point.
Okay.
And then at that point, if you go out left and right, you still go up.
Exactly, right? So this is a saddle point because it's like we're going up. So moving this way, it's like you got a high point here, and then now you're going back down again. But then from there, it's like a low point in this direction, right? So it's like a saddle. So this is like going down to here and then back up this way. So that's right there is a saddle point. Good. All right, what about here? Chauncey, what'd you guys say about?
It looks like a minimum point.
Minimum or maximum? Minimum, because from here, direction of greatest rate of change is always away from that point. So you got a local minimum there. And then finally here, think about right here. David. Another saddle. So in this direction, minimum or maximum? If you're traveling in this direction, that's min or max? What's that? Min, and then if you're traveling this way, max. Right? So it's a saddle. Okay, so if it's a min here, so it's like you could sit in that thing facing this way, right? You could sit. Your legs would hang over this way. You could face this way, and you'd be sitting in the saddle going to the right. Okay, so now remember we talked about a contour plot. So then a gradient field becomes a way of representing a surface, right? So this is a representation of the surface or the potential function from which it came. So another way that we represented surfaces was through a contour plot. So what would the contour plot, how would the contour lines and the contour plot then relate to the gradient field? What would that be like? Remember how the relationship between the gradient vectors and contour lines was? Yeah, Eric? The contour lines are orthogonal. Because remember, the direction of greatest rate of change was orthogonal to direction of what? What about the rate of change? Zero rate of change, right? Constant function value, right? Because so if you stay in the contour lines, you have zero rate of change. You're staying at a constant z. And that's exactly orthogonal to direction of max change. So could you imagine what the contour plot looks like for this? For instance, here in this first quadrant, what would the contour plot look like? Julia, what do you think?
Probably the concentric rings that get closer together as you get towards that center.
Okay, so concentric rings that get closer together towards the center. What do you guys think? So rings that are closer together means greater rate of change or lower rate of change? Greater. So towards the center, wider part, right? The greatest, the rings would be closer away from the max, right? Because you'd have the steepest here, and then it would be less rate of change, and then so you have the rings would be furthest spaced near the local max, and then as you moved away from the local max, they'd be closer together. Does that make sense? And then what about here? What would this look like compared to the contour plot for that? For the local min? What's that? Yeah, it would look the same. It would look the same to you. And so only with the gradient field then would you be able to tell, or some values on the contour lines, whether it was a local max or min. All right. So, and then we know with the saddle points, we would just have to kind of draw the contour lines. We'd have to draw lines that are always perpendicular to the vectors, right? So we might have rings like arcs like this, and then we might have arcs like this, right? So arcs this way. So it's going to be like arcs, I don't know, concave towards that saddle or something like that. Anyway, here it is. So that's the same. That's the image of the contour plot for that gradient field, and all the gradient vectors are all orthogonal to the contour lines. So then, what is the surface then? What? Now we've talked a lot about the surface without looking at it. So can you imagine the surface? Could you explain it? What would it be like? So and this just keeps repeating. So if I could show you more of it. This pattern just keeps repeating over and over again.
Looks like an egg carton.
Yeah.
An egg carton, very good. And this is actually the graph of sine x plus sine y. So I could show, let's reset the graph here. There we go. Okay. All right, questions on that? Okay, cool. So that is our, so we talked about this idea of if you have a gradient field, then there's this function from which it came. So let's talk about this. So if I had a vector field, two comma y. So could we find the potential function from which it came, right? So could we find the potential function from which it came? So if this was a gradient field for some potential function f, so it's like, so what is f? F. Okay. What would the 2 be? What would the 2 be if this was a gradient field? No, what is the 2? What is it? What is it? Partial with respect to x. That's what that is. That's the partial with respect to x. And the y is? Partial with respect to y. So what we can do is, if this is the partial with respect to x, we can get an idea of what the potential function is by doing what? So if f of x, xy equals 2, then from that we can get an idea of what f of xy is. How? Antiderivative with respect to x, right? So if this means that when we took the derivative, the partial derivative with respect to x, we got 2. So we're going to do like kind of the partial antiderivative. All right, so that would be that 2x. Now we got to. So there's a little bit more to this, right? So we know that there would have to be a 2x in this function. But then what else? So the plus c then really has more stuff in it than just a constant, right? Yeah, so exactly. So we could have like any function of y. Any function just of y would still give us a partial derivative with respect to x of 2. That makes sense? Because it would just go be 0. So yeah, so we'll say g of y. And then we could also have a constant. So if the partial derivative with respect to x is 2, then the original function would have to be of this form. Now that the c could be 0 and the g of y could be 0. But this would be kind of the form of what the original function has to look like. Okay? So now we also know that the partial with respect to y equals y. Okay? Now this can give us another perspective on f, right? So when we do the partial, when we do the partial antiderivative with respect to y, we're really like getting a different perspective on the same function f, right? We're still talking about f. These aren't two different functions. It's the same function. It's just a different view of it, right? Because we have different information from each partial derivative. Okay? So if it were partial, if we just had a y, that would mean what? We'd have y squared over 2, and does that match one of these things here? G of y, right? Then what else could we possibly have in the function f if the partial with respect to y is y? Well, if we didn't know this, right? Just some function of x, right? We could have any function just of x, and we could have a constant. So, if this is a gradient field, that means that we should be able to resolve these into the same function. There should be one function f that has both of these as a way of looking at it. If we can't get these to agree, into the same function, then what does that tell us about our vector field? What's that? Not a gradient field, right? It's not a gradient field. A gradient field is a very special type of vector field. It means it came as the partial derivatives of a function. So you can write all kinds of vector fields that aren't the partial derivatives of a function, and so those are not a gradient field. Okay, so can we resolve these into one and the same function? So this 2x, does it have a home in the other perspective? It could be h of x. The y squared over 2, does it have a home in this one? Yeah, g of y. And then we could have any constant. So, right? Yay. Meaning we have a gradient field, and that gradient field is what? 2x plus y squared over 2. No, plus 96.2 pi. There we go. Right? Plus any constant, right? So it could be any constant will work, right? But you have to have a 2x, and you have to have a y squared over 2. And then, yeah, and so then that's it. Yeah. Yeah, so right. It can be any constant. Any constant will have this as its gradient field. Okay, so now what about example 2? Let's do y comma 1. If that's a gradient field, then our partial with respect to x is what? No, the partial with respect to x is y meaning that that gives us a certain view of this function, which is what? Now we're doing the partial antiderivative, xy plus some function just of y plus a constant. All right, and then partial respect to y is 1, which means if the partial respect to y is 1, that means we have a term that is just y. We could have some function just of x, and we could have a constant. Okay, so what is the potential function? Again, so if this is the partial respect to x and this is the partial respect to y, we need to be able to write f. This needs to show the same function f. So does it? Well, this is good. Smooth sailing here, right? That's fine. We don't have to have a function of x. But then what about this guy right here? Do we have a place for that in our other perspective of it down here? It's not there, right? There is no xy. In order for this to get a partial derivative of x with respect to x, that's why you need to have a term xy. According to the partial respect to y, that's impossible. Right? There is no xy term, because if there was an xy term, then what would we have with the partial respect to y? Plus x, right? We don't have it. So this has no home here. So what does it say? This is not a gradient field, because you can't write a function f that has that as its gradient. So there's no function f such that is the gradient. Therefore, that's a perfectly valid vector field, but it's not a gradient field. Gradient fields are special, right? They come from what we call a potential function, and they're the partial derivatives of that potential function. Okay, does it make sense? Okay, so let's start the next topic, which is line integrals. So line integrals, actually finding a potential function algebraically is not on the test Friday. Okay, doing what we just did here, and line integrals are not on the test Friday. But this stuff is super important for the last month of class and the final exam for sure. All right. So you could argue the line integrals are kind of, maybe this is the first topic in the final topic of the course, which is vector calculus, where we're going to put lots and lots of this stuff we learned so far all together. Everything's going to come together here as we we're going to actually come to the point at the end of the class where we're really looking at the fundamental theorem of calculus for R3, but then it turns out that there's like 4 of them. There's like 4 different fundamental theorems. So that's where we're heading. Okay? So line integrals of f of xy have a form like this. So it's the integral over c of a function f ds. Okay, so these are all symbols we've seen before in Calc 3 and Calc 2. So let's ask, first of all, what is f of xy? What's that? Yeah.
It's like a double integral for partial because x and y. It's partial integral of x and then you take the partial.
No, I'm just asking what f of xy is. I'm just asking. Multivariable function, right? This graphs as surface in R3. This graphs as a surface in R3. Okay? what is C? So we've seen this before. We use this symbol to mean what? Capital C. Yeah, but not. No. Yeah, C stands for a curve, right? C stands for some curve or some piece of a curve. Okay? And that's actually in, so I'll start drawing a picture here. That's actually in R2. So I'll start drawing as we go here. So we got okay, that's the worst surface I've ever drawn. Wow, why am I having so much trouble here? There we go. There we go. Okay. And so that's our F, surface in R3. And then C is actually a curve in the XY plane. And how do we express curves in the XY plane? Yeah, we remember we had what kind of function? So a curve in R2 would be single or multivariable, real valued or vector function. So single variable, vector valued function. Now, yes, single variable real valued functions also give us curves, but since we're dealing in vector calculus, in this case, we're gonna use a single variable vector valued function, right? So that can give us a curve. Last thing is, what is ds? So this is, I don't think we saw this in Calc 3, but you saw this in Calc 2. What does ds stand for? Remember? We had dx and then dy and then ds. Remember what ds is? What's that? Yeah, so it's a little length of the curve, right? So ds is not a little change in x or a little change in y, but a little change in distance along the curve, or a little change in length along the curve. So putting it all together then. So ds then is like a little bit of arc length to be ds. So putting it together then, what is the line integral of, so we're integrating this function f, over c, and we're doing it little bits at a time, over little bits of arc length at a time. So what would that give? Yeah, Simon.
The signed area under the curve to the XY plane.
Okay, under the surface. Okay, and which area underneath the surface? Yeah, so so the curve is going to define the xy points that we want from the surface, and then this integral then is going to give us signed area of those points on the surface, which are right over the curve, to the xy plane, right? So it's going to be something like this. So we're just going to take those points on the surface for those points on the curve, those xy points on the curve. If we integrate those z values over those points on the curve, then we're going to get the signed area of like a curtain, right? It's going to be like the signed area of a curtain. Signed because if f ever goes below, like we've always said, you're going to get a negative contribution to the integral. So imagine like a wavy curtain there, and then determined by C, and whose height is F, determined by C. All right, so then when we solve this thing, we've got what, 3 different variables here. We got S, and we got X and Y. So it's a single integral, so we're going to have to get it down to a single variable to solve it. So what single variable are we going to use? T, because the curve is, if we're going to define that as a function of t. So we're going to rewrite this line integral in terms of t. We've got to get everything in terms of t. So the curve is our r of t. And so then the question is, what is ds in terms of t? So maybe the next thing we could ask is, what would ds dt mean? So ds dt, and now this is something we've definitely seen before. So ds dt this semester would mean what? David, you want to try that? Is that what you're... No? Did you have a question about something? Okay. ds dt. The rate of change of a little bit of arc length with respect to a little change in t would mean what? What is that like? So, little change in arc length for a little change in t. Julian.
Is it like dy dt or dx dt?
Okay, but looking for more like an idea, what its idea is. So that might be a way to get the value, but what's the idea of ds dt? Anybody? Yeah, okay. Arc length per change in our parameter, right? So as t changes, we get points on the curve. So what would a change in arc length per change in t be like? If r was position, right? If r was a position vector function, then what would ds dt be like? What's that? Is that what you're going to say, Andrew? Okay, and so if r was, that's right, so if r was position, ds dt would be? Is it velocity? Velocity is what? Velocity is a vector, right? Is that a ds dt? Is that a vector? Speed, right? So ds dt would be like speed. It'd be like the speed of the curve, how fast the curve is being drawn out per change in t. So it's like speed. So ds dt is the rate of change of length of c for a small change in t, which is like speed. So given rt, what is then ds dt equal to for the function rt if it's speed? Who remembers? Andrew? Magnitude of? The magnitude of r prime. What do you think about that? Ryan likes it. Paul, what do you think? That's what it is, right? So ds dt is, you could rewrite that as the magnitude of r prime of t. Because r prime is our velocity vectors, and we just want just the speed, the magnitude of those. So ds dt. That means that we've got what ds is. Then what is ds for our integral up here? What is ds? If ds dt is this, then ds is multiplied dt, right? So ds is just the speed dt. And so now we know we've got all the tools we need now to solve a line integral, right? To solve a line integral, it would be, we have to rewrite the f function in terms of t, and that would just be a matter of plugging in the components into there. And then for c, we're going to integrate from the starting value of t, say t1 to t2. And ds is magnitude of r prime dt. So there it is. So it's going to be the integral from t1 to t2 of the function written in terms of t, ds, which is our speed dt. And then again, that's going to give us what? That'll give us signed area of this curtain, whose height is on the surface, defined by C. Like it's the way that it goes laterally is defined by C. All right, any questions about that? So let's do an example here. We want this right here. So we want to go. I want to do the line integral over C of x ds, where C is the arc of y equals x squared from negative 1, 1 to 3, 9. So from negative 1, 1, C is going to go from there to 3, 9. So that's our C. Okay, so what's the whole basis of this is being able to write that curve C as a vector function. And we've done this before. So we have some different techniques, right, for doing this. But in this case, what makes the most sense? Harris remembers? Yeah, so we can say x equals, we can just let x be t. And then if x is t, then what's y? So that was one of the techniques we had. In certain cases, it made the most sense just to let x be t, and then in this case, then y is t squared. So there's our vector function. Okay, and so then our limits of integration are going to be from t equals what to what? Negative 1 to 3, because t is just the same as the x coordinate for this point. So we're going to go from t from negative 1 to 3. So we're going to go from negative 1 to 3. So this thing right here. Negative 1 to 3 of x. What's x? T. And then we need ds. What was ds again? Magnitude of r prime. So we got to get r prime of t, which is 1 and 2t. Magnitude is 1 plus 4t squared. So it'll be t times magnitude of 1 plus 4t squared. There's our magnitude of r prime dt. And now we've got a calc 1 integral, right? We got a calc 1 single integral. And how do we do that? Is that an antiderivative we can do? So this is a chain rule. Do you see this is a chain rule derivative? So undoing the chain rule gives us 1 plus 4t squared to the 3 halves. We're going to need 2/3. We're also going to need, imagine taking the derivative of this. It'd be 3 halves times that to the 1/2 times what? 8t. We only have t, so we'll need 1/8. And we're going to evaluate that from -1 to 3. So what is this, 1/12? Minus 1/12 of, I don't want to do any more on that.